conductor surface, electric field is minimum. That means he is talking of tangential component that is 0, that is actually minimum. 0 means minimum here. Okay. And this is objective question. This is standard question. And magnetic field is maximum. That means HT1 bar not equal to 0, that is actually maximum. So here you may confuse. In textbooks they write like this, that is why I am writing. Now what is written there I will explain. On the conductor surface, let us say this is conductor medium. It is very big conductor here. On the conductor surface means this one. So that side what is there? Medium 1 is there. And on the conductor surface means parallel to conductor surface. That is the meaning. On the conductor surface means parallel to conductor surface. What is parallel to conductor surface? Tangential component. So how much tangential component? 0. 0 means minimum. Now electric field and magnetic field, they are 90 degrees to each other. So 90 degrees means if one is minimum, other one is maximum. For example, you take sinusoidal signal. So if you take sinusoidal signal like this, and this is one period, and here 0 degrees, 90 degrees, like 180 degrees, 270 degrees, 360 degrees. This is 0, that is called minimum. At 90 degrees you are getting maximum. So the angle between minimum and maximum is 90 degrees. Like this, here electric field and magnetic field are 90 degrees to each other. So here tangential component of electric field is minimum means magnetic field will be 90 degrees to that. That will be not 0. So maximum ho jata hai wo. You can see here normal component is not 0. Not 0 means maximum. But magnetic field normal component will be minimum again. So like that. So this is standard question, student. So on the conductor surface means that fellow is talking of tangential electric field component and tangential magnetic field component. The derivation is done for tangential electric field component, that is 0. Automatically they don't do derivation for magnetic field component. Simply they write electric and magnetic fields are 90 degrees to each other. If this is minimum, automatically electric field tangential component is minimum. Automatically magnetic field tangential component will be maximum. So these two are standard statements. Now you have to remember this point and this point. My dear student, boundary conditions are very important. Now whatever I have discussed, you release them from your memory. दिमाग से छोड़ दो उसको. Now आप लोग क्या याद रखना है? How to find tangential and normal component I told you. Then after that I wrote 4 boundary conditions. Then after that these 2 points you have to remember. Then overall boundary condition concept is over. Now you will be solving the questions. In the workbook, in first chapter 2 questions are there. In the second chapter 3 questions are there. We will solve them. So anyway student, the first boundary condition is this one, ET1 is equal to ET2. Second boundary condition is dN1 minus dN2 is equal to rho s. These two are called electric boundary conditions. And the third boundary condition is HT1 bar minus HT2 bar is equal to AN12 cross K bar. And BN1 bar is equal to BN2 bar. This is the third one, this is fourth one. These two are called magnetic boundary conditions. These first one and second one are called electric boundary conditions. They give relation between electric fields of medium 1 and medium 2. These third one and the fourth one are called magnetic boundary conditions. They give the relation between magnetic fields of medium 1 and magnetic fields of medium 2. So if anybody asks you single statement, what are boundary conditions? Boundary conditions give tangential relations for intensities and normal relations for densities. It is that simple. We will solve the questions. Okay. So dear students, now let us solve this question. I am not writing the question number. This is chapter 1 question because different students have different question number. A homogeneous dielectric epsilon R1 is equal to 2.5 fills region 1, that means medium 1, that is x less than 0, while region 2, that means medium 2, that is for x greater than 0 is free space, full stop. If d1 bar is equal to 12ax minus 10ay plus 4az, that is not a2, that is az, nanocoulomb per meter square, find d2 bar vector and theta 2. Now what is theta 2? It is given where theta 2 is angle made between d2 bar and the surface. d2 bar and the surface. Here surface means boundary surface. So this is the question. Now let us solve, students. For example, let us take boundary surface like this. He has given x equal to 0 surface. You can take like this also or like this also, doesn't matter. So if you take the boundary surface like this, so let us call this is x equal to 0 boundary surface. Now let us say this is x greater than 0. So here medium 2 is there and x less than 0, medium 1 is there. Here he has given d1 bar. Now you draw this one. This line is called normal an1 to normal unit vector from medium 1 to medium 2. Of course that is ax cap actually. You see x less than 0, x equal to 0, x greater than 0, x value is increasing like this. So that is ax cap actually. Ax cap. Anyway, now he himself saying this d1 bar vector, this is d1 bar vector and some d2 bar vector, this is a d2 bar vector. He himself saying theta 2 is angle between d2 bar and the surface, that means this surface, boundary surface. This is surface, boundary surface. So theta 2 is angle between the d2 bar vector. I will draw the arrow mark here. I am writing here d2 bar vector. This d2 bar vector and the surface making theta 2 angle is given, theta 2. Now we have to find what is this d2 bar and what is this theta 2, and he has given this region 1, this is medium 1, epsilon r1 is equal to 2.5 and second medium is free space, that means this is air medium. So epsilon r of that is epsilon r1 is equal to 1 for that. Till now I was telling you that here I am writing for x equal to 0 boundary x component is a normal component. So it is normal component. That means dn1 bar is equal to 12ax. Now what is tangential component? That is minus 10 ay plus 4 az. So here nano coulomb per meter square is there. So here also nano coulomb per meter square is there. Nano coulomb per meter square. So this is d t1 bar, this one. So if this x component is normal component, remaining are tangential component. Okay. Now the first boundary condition, because electric fields in medium 1, electric fields means E bar, D bar, they are commonly called as electric fields. Electric fields in medium 1 are given. You have to find fields in medium 2 electric fields. So first and second boundary conditions are used. First boundary condition is ET1 bar is equal to ET2 bar. Okay. Now actually D2 bar is equal to, here I am writing D2 bar is equal to DT2 plus DN2. If you want D2, find this separately. Now you want D2 bar. So write this in terms of D. Electric field is equal to D bar divided by epsilon. For medium 2 it is 2 and DT2. Similarly, ET1 is not given, DT1 is given. Write this in terms of D. So E is equal to D by epsilon, that is for medium 1. So this one. Now from this DT2 is equal to epsilon 2 by epsilon 1 dt1. Now dt2 is equal to epsilon 2 is epsilon naught into epsilon r2. This is medium 2 na student. So epsilon r2 is equal to 1 because it is given region 2 is free space is given. So that is epsilon 2 is epsilon naught into epsilon r is 1. Epsilon 1 is epsilon naught into epsilon r1 is 2.5. 2.5 means 5 by 2. And dt1 is given here minus 10 ay plus 4 az nano coulomb per meter square. So 2 by 5. Epsilon naught cancel. So dt2 is equal to 2 by 5. 2 by 5 na minus 4 ay. Then 2 into 4 8. 8 by 5. 1 time 30 is there. 6 na 1.6 az nano coulomb per meter square. So let us say this is equation number 1, this one. Now let us say this equation number 2. Second boundary condition is dn1 bar is equal to dn2 bar in this case, because rho s is not given, so rho s is equal to 0, because in this question rho s is not given. So that means dn2 bar is equal to dn1 bar is 12ax, so 12ax nano coulomb per meter square. So put 2 comma 3 in 1. So now d2 bar is equal to that is 12ax minus 4ay plus 1.6 az. So this is nano coulomb per meter square. So this is the d2 bar, 12ax minus 4ay plus 1.6 az. So this is that one. Now we have to find theta 2. So students, you know that this vector has a tangential component and normal component. Tangential component means the component which is parallel to the boundary surface. This is boundary surface. So this one is a tangential component dt2, and this one is 90 degrees to the boundary surface. So that is called normal component. Now tan theta definition is equal to opposite by adjacent. but you have to take mod because tan definition is done with magnitudes. So tan theta 2 is equal to opposite is modulus of dn2 divided by modulus of d dt2. So okay, um, tan theta 2 is equal to modulus of dn1, modulus of dn2. Modulus of this is root of 12 square is 12 divided by modulus of dt2, this one. Root of minus 4 whole square means 4 square plus 1.6 whole square. Now you get this 12 by 4.3081. Ultimately, from this you get theta 2 is equal to 70.25 degrees you get. Okay, that is the answer. Now, next question. Two dielectric media means plural of mediums, that is media with permittivities 3 and root 3 are separated by a charge free boundary as shown in figure. Separated by a charge free boundary as shown in figure. The electric field intensity in medium 1, the electric field intensity in medium 1 at point P1 has a magnitude, he has given E1, I am putting as modulus of E1 bar, magnitude is modulus of E1 bar, and makes an angle alpha 1 is equal to 60 degrees with the normal. That means with the normal means normal unit vector to the boundary. The value of alpha 2 is, so the boundary is given here. The diagram is given like this. I am drawing here. So this is the normal, students. Now the electric field E1 magnitude of that is given like this, and it makes 60 degrees here, alpha 1, and here E2 bar is given magnitude and alpha 2 is there. You have to find that alpha 2. So here this medium is first medium, so epsilon R1 is equal to 3, and this is second medium, epsilon R2 is equal to root 3. So this much is given. Now what to do, student? Here the angle is there. So what I will do? I will do like this. I can write this here or otherwise here, no problem. So anyway, I will write this here, modulus of E1 bar. This is modulus of E1 bar. Now this has a tangential component. So this one is parallel to this boundary. I will remove this. I want some place. This component is parallel to this, so that is called tangential component. That is actually modulus of ET1. So this one is 90 degrees to the boundary, so that is called as modulus of En1 for first medium. Okay. Similarly, if I draw this one, this is actually parallel, so modulus of ET2, and this one is modulus of E into normal component. Now, from the Pythagoras theorem, this is hypotenuse opposite to 90 degrees. This is hypotenuse, and this one is touching the angle, so this is adjacent. Mod En1 is equal to modulus of E1 cos 60. This is opposite. This is modulus of E1 into sin 60. Similarly, this is opposite. So that is nothing but modulus of E2 into sin opposite, na? So sin alpha 2. This is adjacent touching this one. So modulus of En2 is equal to modulus of E2 into cos alpha 2. Okay. Now, first boundary condition. First boundary condition is Et1 is equal to Et2, and in mod form also they are equal. Modulus of Et1 is equal to modulus of Et2. So here modulus of Et1 is this one. That means modulus of E1 sin 60 is equal to modulus of Et2 is this one. So modulus of E2 sin alpha 2, this is equation number 1. Similarly, second boundary condition is second boundary condition is dn1 is equal to dn2. That dn1 is equal to epsilon 1 into en1. En1 is nothing but this one. So modulus of E1 into cos 60 degrees. dn2 is equal to epsilon 2 into en2. So this en2 is modulus of E2 into cos alpha 2. This is equation number 2. Now you take the ratio of them. Equation 1 divided by equation 2 gives that is modulus of E1 sin 60. This is modulus of E2 sin alpha 2. This one epsilon 1. Epsilon 1 is nothing but epsilon naught into epsilon r1 is 3. Then this is modulus of E1. Modulus of E1 cos 60. Then that is equal to this one epsilon 2 is epsilon naught into epsilon r2 is root 3. Then modulus of E2 and cos alpha 2. So modulus of E1 cancel, modulus of E2 cancel, epsilon naught cancel, sin by cos is tan. So tan 60 divided by 3 here is equal to tan alpha 2 divided by root 3. Now tan alpha 2 is equal to root 3 goes that side, root 3 divided by 3, tan 60 is again root 3. So root 3 into 3 1. So tan alpha 2 is equal to 1 and alpha 2 is equal to 45 degrees you get. So that is the answer. Okay. So in this way, whenever you see, dear students, in any question epsilon 1 epsilon 2 or otherwise mu 1 mu 2, like this you see medium 1 medium 2, automatically you should think that they are boundary condition questions. In any question you see medium 1 and medium 2 or otherwise epsilon 1 epsilon 2 mu 1 mu 2 like that, they are automatically boundary condition questions. If you recall the boundary conditions, then those questions will be solved. अगर कोई क्वेश्चन में आप मीडियम 1 मीडियम 2 देख लिया या एप्सिलॉन 1 एप्सिलॉन 2 या म्यू 1 म्यू 2 देख लिया, वो क्वेश्चन है बाउंड्री कंडीशन रिलेटेड वाला है. सो बाउंड्री कंडीशन यूज करना है करके दिमाग में आइडिया आ जाएगा, वो क्वेश्चन आपने आप सॉल्व हो जाता है. ठीक है स्टूडेंट, ठीक है. सो अभी हम इलेक्ट्रिक बाउंड्री कंडीशंस का बेसिस में क्वेश्चन सॉल्व किया और मैग्नेटिक बाउंड्री कंडीशंस का बेसिस में चैप्टर 2 में है क्वेश्चंस, वो 3 क्वेश्चंस वो भी सॉल्व करेंगे. स्टूडेंट्स, नाउ लेट अस सॉल्व मैग्नेटिक बाउंड्री कंडीशन क्वेश्चंस. सो दिस इज इन चैप्टर 2 क्वेश्चन. A sheet J bar 10 UY cap ampere per meter. That means this is surface current density actually, because ampere per meter means that is surface current density, student. Lies, that is why sheet is given. Sheet means surface. Lies on the dielectric interface. Dielectric interface means boundary only. Interface x is equal to 0 between two dielectric media with epsilon r is equal to 1, mu r epsilon r1 is equal to 1, mu r1 is equal to 1 in region 1. Region 1, that means medium 1 for x less than 0, and epsilon r2 is equal to 2, mu r2 is equal to 2 in region 2 for x greater than 0. If magnetic field in region 1 if magnetic field in region 1 of course that is in region 1, student. If magnetic field in region 1 at x is equal to 0 minus means just near the boundary. 0 x equal to 0 means exactly on the boundary. X equal to 0 minus means just below the boundary. X equal to 0 plus means just above the boundary. That comes medium 2 actually. Is H1 bar is equal to 3 UX cap and 30 UY cap ampere per meter. The magnetic field in region 2, the magnetic field in region 2 at x is equal to 0 plus is, that means just above the boundary is asking. So it is given that this he is saying x greater than 0 region 2, that means that is dielectric 2 having epsilon r2 is equal to 2 and mu r2 is equal to 2, and of course this is x equal to 0 boundary. Now x less than 0 is region 1. Here epsilon r1 is equal to, here 5 is printed, there 1 is given it seems. Anyway, you write 5 and mu r1 is equal to 1. We are not bothered about this epsilon r because this is a magnetic fields are given. So we don't use this epsilon r's. Mu r's only we will use. Okay. So this is the question. He is saying this is also dielectric, this is also dielectric, but here thin conductor surface is there. That conductor surface is carrying the J bar surface current density 10 UY cap ampere per meter, that is surface current density is present on this conductor sheet. That conductor sheet is separating dielectric 1 and dielectric 2. X equal to 0 means this one. X equal to 0 minus means just below this conductor sheet, that is medium 1. X equal to 0 plus means just above the sheet, that is medium 2. So what is given is H1 bar is given, that is in medium 1 it is given. So H1 bar is given, that is 3 UX cap plus 30 times UI cap ampere per meter is given. Now let us start the solution. For x equal to 0 boundary, x component is normal. That means Hn1 bar is equal to 3 times Ux cap. Then you leave this one, isko chhod dijiye. Then whatever remains that is called Hn1 bar, that is 30 Ui cap. Now Third boundary condition is ht1 bar minus ht2 bar is equal to an12 cross k cap. Now what is an12 here? Normal unit vector goes from medium 1 to medium 2. So that is an12 here. So this makes 90 degrees with this boundary surface. Then going from medium 1 to medium 2, this is less than 0, this is greater than 0. That means x value is increasing in this direction. Ax cap is unit vector in the direction of increasing x value. So here an12 is Ax cap actually. Then you want ht2 here, because you have to find h2 bar. H2 bar is sum of ht2 and hn2. So you have to find ht2 and hn2. From this ht2 you can find ht2 is equal to, this side you get that, minus an12 cross k. Here ht1 is given here, this one. No, this one is ht1 student. Because normal component is x component, remaining is tangential component. ht1 is that one. 30 times uy cap minus an12 is ax cap cross k bar means that is j bar is given. Don't bother about this symbol, student. See the unit and decide what is that. Unit is ampere per meter, that is surface current density, 10 uy cap. So I am taking here ax cap as ux cap. ux cross uy, 30 uy cap, ux cross uy is nothing but uz. So this is ht2. This is equation number 2. Now fourth boundary condition is bn1 bar is equal to bn2 bar. This is mu1 hn1 is equal to mu2 hn2. That implies hn2 is equal to mu1 by mu2 hn1 bar. So hn2 bar is equal to mu1 is mu naught into mu r1. So here mu r1 is 1 divided by mu naught into mu r2. Mu r2 is equal to 2 actually. And hn1 bar is equal to this one, 3 times ux. So you get 1.5 ux cap. So this is equation number 3. Put equation 2 comma 3 in equation number 1. Then you get h2 bar is equal to 1.5 ux cap plus 30 times uy cap minus 10 uz cap. So this is the answer. Now it is in option A. So option A is correct for this. Okay. Now next question. The magnetic field on either sides. On either sides मतलब दोनों sides है. On either sides of two materials, that means mediums there, two materials are h1 bar is equal to 14 ax cap minus 5 ay cap plus 21 az cap, and h2 bar is equal to 3 ax cap minus 3 ay cap plus 3 az cap. The boundary is parallel to one of the coordinate axis. That means the boundary may be x equal to 0 or y is equal to 0 or z is equal to 0, any one of them. Okay. Which of the following statements are true? Which of the following statements are true? Okay. Now, before solving this question, let us discuss one thing. That is, third boundary condition is ht1 bar minus ht2 bar is equal to an12 cross k. Students, if k bar 0, then ht1 and ht2 both will be equal, student, if k bar is 0. If k bar is not 0, then ht1 and ht2 are not equal. That means they are unequal. Similarly, let us write the another boundary condition. bn1 bar is equal to bn2 bar is another condition. mu1 hn1 bar is equal to mu2 hn2 bar. That means hn2 bar is equal to mu1 divided by mu2 hn1 bar. From this, now, if hn1 is equal to hn2, then mu1 is equal to mu2. Of course, we can write like this also. If in any medium hn1 bar and hn2 bar are unequal, that means both mediums have different mu values. That is the meaning actually. This is general discussion. Now let us go to the question. Let now answer we are discussing. So let x equal to 0 is the boundary. Then x component is a normal component, students. So that means hn1 is equal to 14ax, then remaining ht1 is minus 5ay plus 21az. Similarly, hn2 is equal to x component is normal component, that is 3ax, and ht2 is equal to minus 3ay plus 3az. Now, if you see this one, hn1 and hn2 are unequal. This is 14, this is 3. That means here hn1 not equal to hn2. That implies mu1 not equal to mu2. That means both mediums have different permeabilities. And also you see this one, minus 5, minus 3, they are not equal. 21, 3, they are not equal. That means here ht1 is not equal to ht2. That indicates that k bar is not 0. You can see here, if these two are not equal, then k bar is not 0. That means on that boundary surface, surface current density is present. If you see the options, then option B, it is correct option, that the boundary is having surface current. So that is the answer. The boundary is having surface current, or otherwise surface current density is there. So that is the answer. Okay, student. Now, even if you take y is equal to 0 boundary or z is equal to 0 boundary, for all the cases, ht1 is not equal to ht2, because ultimately these two are not at all equal, these vectors. So that is the answer, students. Now, another question. The question is like this. A region shown below contains a perfect conducting of space and air. That means one side conducting medium is there, other side air is there. Full stop. The surface current Ks bar, that is surface current density on the surface of the perfect conductor is Ks bar is equal to 2 times x cap ampere per meter. That means you see, don't see the symbol. See, the unit is there in ampere per meter, and current, that is then automatically it is surface current density. Now the tangential h bar, that means ht field in the air just above the perfect conductor is. So here is this diagram. Actually it is given like this. It is perfect conductor and this one is air. Now surface current density Ks bar is going on the surface, and this is, he has given this normal unit vector to this is y, like this. It is given y na here, y. Now in this medium you have to find tangential component. So what is which is medium 1 and which is medium 2? You can take any one as a medium 1 and the other one as medium 2. Not given means you can take this as a medium 1, you can take this as a medium 2. Otherwise you can take this as a medium 1, this as a medium 2. In both cases you get same answer. Let us take this as a medium 1 and let us take this as a medium 2. Then that means he is asking tangential component of h in the air means you need ht2 bar is required. You have to find ht2. Now air is medium 2, you need tangential component ht2 is required. Now already I have explained, na student, inside the conductor total electric field is 0, then this electric field generates magnetic field. If electric field is 0, then total magnetic field is also 0. Then total magnetic field 0 means magnetic field tangential component, magnetic field normal component, they are 0 inside the conductor. So now dear students, the condition which gives tangential relations is ht1 bar minus ht2 bar is equal to an12 cross k bar. Now you send this side, so ht2 is required, then ht1 minus an12 cross k bar. Now what is an12 bar? Let us see. You have to remember the definition of that an12 bar. an12 bar means normal unit vector to the boundary surface going from medium 1 to medium 2, and that makes 90 degrees to this boundary surface. That is this one. That is the definition of an12 bar. an12 bar definition is normal unit vector to the boundary surface from medium 1 to medium 2. Now upwards it is given y axis, so that is ay cap, and here x cap, y cap, z cap is used, so it is y cap. Now notation is used y cap, so that is nothing but ay cap only. Okay. Now here any print means, yes, it is conductor is medium 1, so E1 bar is 0, and inside the conductor electric field 0, magnetic field 0. So I have taken this as a medium 1, student. Now that is equal to total magnetic field in conductor is 0, that means this is also 0, tangential component is 0. an12 is y cap cross k bar is given as 2 x cap. So that is equal to minus of 2 into y cross x is minus z cap. So that is nothing but 2 z cap is the answer. Okay, students. So this answer is in option D. Option D it is. So this is the answer. Okay. So dear students, this is time varying fields and Maxwell equations. In this first one is Faraday's law. So Faraday did one experiment from that experiment, he gave one equation and he gave one statement also. What is the statement of that experiment? Faraday's law states that the time varying magnetic field produces an electromotive force EMF. This EMF produces current in a closed path. Otherwise, it is written like this also. EMF around a closed line is equal to the time rate of decrease of magnetic flux passing through a surface enclosed means inside, that surface is inside the closed line. Okay, mathematically EMF is equal to minus of d by dt. Total magnetic flux is n into pi if n turns are there, and this is volts. EMF is volts actually. So here n is number of turns. For single turn or otherwise for single loop n is equal to 1. So EMF is equal to minus of d pi by dt volt. This is equation number 1 for single turn. So what it is saying, student, EMF around a closed line is equal to the time rate of, that means d by dt means time rate, minus means decrease of magnetic flux passing through a surface enclosed by that closed line. Whatever closed line you take, that one you will see one picture, in that you will understand that more clearly. So in this one here minus sign is there. Minus sign is due to Lenz's law, which states that the induced EMF opposes the changing magnetic flux, or otherwise opposes the increasing magnetic flux. That is actually conservation of energy. Energy can neither created nor destroyed. I will explain that, don't worry, I will explain that. Actually what this statement says, I will take one example 1. For example, here in example 1, conductor loop is not moving. Okay, in a conductor loop is there, here it is not moving. Then you take one magnet here, and this is north pole and this is south pole. So this magnet is moving upwards. So moving magnet it is. So if this magnet moves upwards, then original magnetic field B original, that means B bar original magnetic field increases in this direction because it is moving like this means it is going like this means B bar value increases when you go towards this conductor loop. This loop is like this actually, like this, but on the board it is like this. Actually, this is like this. So here, this is the magnet, student, and this is the conductor loop. When this magnet moves towards this, in this direction, magnetic field increases. So original magnetic field increases in this direction, Now it has some energy. The energy of this one produces EMF in this conductor loop. So then EMF means voltage. Because of that voltage, current is produced. That is called induced current. That means this loop is receiving energy from this one. That is why the energy of this should be decreased. That is why you give the opposite sign for the induced current and induced EMF. That is why you have to give opposite sign. That means you are giving opposite sign means the original value is decreased because this is receiving energy from this one. That's what Lenz's law says. Energy can either created nor destroyed. Now in this actually the induced field will be opposite to the original one. I am writing here B induced is opposite to this one, and induced current is also like this. Induced current is like this. So you use thumb rule, put the thumb in induced magnetic field direction, then in closed finger direction induced current is there. Okay, students. So the original magnetic field direction is increasing like this. Then induced magnetic field, this is generated by induced current. This induced current generates magnetic field, that is called induced magnetic field, that is opposite to the original one. Okay. Similarly, if I take example 2, conductor loop is not moving here. Conductor loop is not moving. Okay, here one conductor loop is there, it is not moving. Now I will take one magnet here. Now this magnet is moving, because of that a changing magnetic field comes. So if something is moving, then magnetic flux density changes with respect to time. So here let us take that this magnet is moving downwards. So this magnet is moving, I will write here, moving upward. This magnet is moving downward. If this magnet moves downward, then original magnetic field increases in down direction, it increases. So then induced magnetic field will be upwards. So B induced is opposite to the original magnetic field. So original magnetic field is moving downwards, so this is upwards. Now put the thumb in original magnetic field direction, then this induced current will be like this. Induced current is like this. So these are examples based on the Lenz law actually. Now you can see here this EMF is present whenever d pi by dt is not 0. So d pi by, that means d pi by dt is non-zero in the following cases. Okay, case 1. Actually Michael Faraday did 3 experiments, that is case 1 one experiment, case 2 second experiment, case 3 third experiment. In all the experiments the EMF is produced. Then case by case, first case is that a non-moving loop area a non-moving loop area is present in the time varying magnetic field. So a non-moving loop area is present in the time varying magnetic field. Then EMF is induced in the loop. This EMF is called as a transformer EMF. Here energy is transformed from time varying field to the loop, actually non-moving loop. So energy is transformed here. That is why transformer EMF. I will take one example. Here let us say one time varying voltage source is there, V of t, like this. Then this is connected to one conductor like this. Then time varying current is there, I of t. So that loop is like this, actually conductor loop. Then this time varying current generates a time varying magnetic field. You put the closed finger in current direction, then time varying magnetic field is generated here in this direction, like this, like this, like this. Here time varying magnetic field is generated. So this time varying magnetic field B of t, it is original magnetic field, actually. Original means the actual source is there for this. Actual source is here, time varying current. This is original current, original voltage source, original magnetic field is there. Original means really source is there for that magnetic field. That is the meaning. Now I will take one conductor having some resistance. So dear students, it is like this, student. You take one conductor, and for this conductor it is a normal conductor. Normal conductor means it is not a perfect conductor. So for normal conductor, here some resistance is there, here also it is there, 0.1 ohm, here also 0.1 ohm. At every location resistance is there. You add total resistance, let us say total resistance of this is 2 ohms when it is drawn like this. Perfect conductor having 0 ohms, then at single location total resistance is 2 ohms. It is shown like this. So that is why in the textbooks, if they give like this, means here perfect conductor is there, the resistance of that 0 ohm, at single location total resistance is 2 ohm, like this it is given. But in any question, simply if they give like this, that means resistance of this is not given, means you have to assume that is a perfect conductor. Now the resistance of this is taken as 0 ohms. Okay, student. Okay. So in the questions, if they give like this, means this is perfect conductor and having 2 ohms at single location. In the question, if they give like this, means this is perfect conductor, total resistance is 0. That is the meaning of that. So here one loop is taken like this. One loop is taken like this, that has some resistance here. Now, if this is the original magnetic field, then induced magnetic field is the opposite of this. That's what Lenz law says. So, in this induced magnetic field is opposite to the original magnetic field. And if you put the right hand thumb in induced magnetic field direction, then automatically in closed finger direction, induced current is present. Induced current is present. Now, in this induced current goes like this, then EMF will be minus plus EMF is produced like this. EMF means voltage, actually. So EMF is nothing but voltage, but that is newly produced voltage. Newly produced voltage because of some effect, actually. So here how many turns I have taken? 0 turn, single turn is there. So for this case, n is equal to 1 you have to take. One important point I am telling you, student. Let us take this is the direction of the magnetic flux density, original magnetic flux density, this one. Now this is the conductor loop. If this conductor loop is like this, then inside this loop there is some area. Through that area, these magnetic field lines upwards, they are crossing that, then only EMF is induced in this loop. For example, if this loop is like this, that means if this loop is parallel to the magnetic field lines, then no magnetic flux crosses the area of this loop. So then in this conductor loop, EMF is not induced. This is very important point you have to remember, my dear students. Once again I am telling, this is original magnetic field direction. So this is magnetic field lines like this, like this, like this, like this, everywhere they are going. Now for example, if I take one conductor loop, this one is conductor loop that has some resistance. If this conductor loop is parallel to the magnetic flux, then no magnetic flux crosses the area of this loop, or otherwise no magnetic flux is present inside this closed loop. So in this, EMF is not generated. That is one case. Now next discussion. If this is the magnetic field direction, then I have taken one conductor loop. That conductor loop is perpendicular to this magnetic field. Now inside this loop there is some area. Through that area, now here zero magnetic flux crosses, so no EMF. Here one magnetic flux line is passing through that area of the loop. That one magnetic flux line generates EMF in this. Now two magnetic flux lines are passing through this area which is present inside this loop. Then both magnetic flux lines generate EMF in this loop, like that. If more magnetic flux passes through the area which is present inside this closed line, then more amount of EMF is produced. The discussion is like this. Here itself it is there. If magnetic flux is more, then EMF is also more. Okay. Now, here how much EMF is produced? Students, in case 1 and case 2, I am going to draw the diagram and I am going to write the equations also. You have to remember the diagram and equation carefully. In examination, you get the this diagram, you have to use that particular equation. You have to remember that. So here, how much EMF is produced? Then answer minus of d pi by dt. So this is the equation here. Because n here single turn is there, so n is 1 is taken. If magnetic flux inside this loop is known, then you put that here, then you get EMF. But in general, they give B bar equation. Given B bar equation, how to get magnetic flux? Already we wrote that. Given B bar, then magnetic flux crossing the open surface is magnetic flux is equal to double integral B bar dot ds bar. So where is that surface actually? I am drawing here this one, na? I am drawing that loop here. So inside this closed loop, this is the area of the surface, that is pi a square. If a is the radius, that is the area. That area is this one. Okay. Now in general, that B bar is uniform actually. So if B bar is uniform, then magnetic flux is equal to B bar dot double integral ds bar. So magnetic flux is equal to B bar dot S bar. Now let us expand that A bar dot B bar formula, modulus of B bar, modulus of S bar, cos of angle between B bar and S bar. So this is simply written as B. This is area of the loop, and then cos theta Bs. So this is magnetic flux, this equation number 2. So if in any question B bar is given, that B bar is uniform. Uniform means not a function of distance. Then if you put this equation here, then you get EMF. Actually, in the examination, they give B bar and they give area, then they give angle between them. So when you want to calculate magnetic, you want to calculate a EMF, then you have to use this equation. For that, you have to put equation 2, put equation 2 in 1, then EMF is equal to minus of d by dt. So B into area into cos theta bs. So this formula is to be used. So this is this is equation number 3. Okay, this is to be used. So for this one, I am drawing a diagram here. For example, here there is one loop like this. Okay, inside this loop, one area is there. This is that area. Now normal unit vector to this loop is like this, n cap, like this it is. Now there is a B bar, that B bar makes some angle with this, that B bar. So theta bs this is. No place here. So I will draw the diagram here. So if there is a this is blue one is a loop actually. Inside that loop there is one imaginary area. That area is this one. The normal unit vector to that area is an cap, because the surface vector is equal to area of the surface into normal unit vector. Now here magnetic field source is there. That magnetic field is making some angle. So this angle is called theta bs. So angle between B bar and S bar. So S bar is normal to this surface. That is the definition. S bar is equal to area multiplied with normal unit vector. Okay. So surface vector direction is an cap, this one, normal to the surface here. If there is magnetic field source that is generating magnetic field in this direction, then angle between B bar and S bar is this is the value that will be given in the question. So then you have to substitute, if 30 degrees angle, then you have to substitute 30 degrees here, students. Okay. Now no need of this one here. Now whenever they give a time varying magnetic field and they give the angle, then you have to substitute this angle here. Here area is pi r square. So here r is the radius of this loop, then pi r square is area, then B of t equation will be given. And if there is a square loop of width a, height b, then area becomes a into b. Okay, students. Okay. Next, if B bar, that means this one, is perpendicular to loop area, then if B bar is perpendicular to loop area, then S bar is also perpendicular to loop area. And S bar is also, that is definition, perpendicular to loop area. So B bar comma S bar are parallel to each other. So theta bs becomes 0 in this case. If theta bs becomes 0, then cos 0 is 1. Then simply EMF is equal to minus of d by dt, and B, of course B of t is written. B of t means it is a function of time. B of t into area. So this formula is to be used in that case. This equation number 1. For this, if you want diagrams, I will draw like this. They give one conductor loop here. So this is conductor loop. Conductor loop is given like this. Maybe circular loop or rectangular loop, doesn't matter. This has some resistance. So this is conductor loop actually like this. This has some resistance. Now if magnetic field is like this, that is into the board, or maybe magnetic field is like this out of the board, then in both the cases here EMF is induced in this, then the formula of that EMF is this one, d by dt. B of t means how much B of t is there, substitute. Area in this case is, if this is A and if this is B, then the area is A into B, how to put here. So whenever you see this type of pictures, you have to use how much EMF induced here, how much EMF induced here. So to find how much EMF induced here, you have to use this formula. So if it is circular loop, then in place of area pi r square you have to use, student. So my dear student, be careful. If you see any question related to time varying fields, don't ask me explanation. You have to remember the pictures. Simply, if you see this picture in the question, you have to pick up the formula, then question solution will be over. No need to think anything. So if you see this type of picture having some angle between B bar and A n cap, you have to use this formula. What is there to explain? Nothing is there. So here you remember one thing, cos is coming, sin is not coming. Why cos is coming? Because from dot product explanation, cos is coming. A bar dot B bar is equal to modulus of A bar modulus of B bar, cos of angle between A and B. So cos is coming, and later on also this equation is required. You put that in your mind. आपका दिमाग में रखो वो चीज को. So ये खत्म होने के बाद, by definition EMF is equal to, by definition EMF is equal to closed E bar dot dl bar. This is also one of the formula. So what is this formula? Let us see. Dear students, actually voltage is equal to minus of integral E dot dl. Then if there is a closed line, you have to put circle. But voltage and EMF is opposite of voltage from the Lenz law. So EMF is minus of voltage. You do minus of, then minus goes here. So induced voltage is opposite to the original voltage. Induced current is opposite to the original current. Induced magnetic flux density is opposite to the original magnetic flux density. So EMF is induced voltage. So induced voltage is opposite to the original voltage. That is why minus sign is not there. So in the textbooks, they write like this. By definition, EMF is equal to closed E dot dl. Why are you taking closed? Because here we have taken closed line. That is why. So inside this closed line, that is the closed line, students. So this is one formula. EMF is equal to closed E dot dl. Okay. Here that EMF, this EMF has two formulas. If you know B and area, then this also gives that EMF. If you know electric field, then closed E dot dl you do. Then also you get EMF. This EMF and that EMF will be equal, dear students. Okay. Now I will write here one observation. Okay, no problem. I will write here one hint. I will write hint, student. What is that hint actually? I will write the hint here. You students know that F bar is equal to Q into V cross B. This formula already you know. This is nothing but force on Q charge moving with V velocity in the magnetic field. This is the formula. Now F bar divided by Q is equal to F bar by Q is equal to V bar cross B bar. Now this is nothing but E bar. E bar is V bar cross B bar. So velocity cross B bar gives electric field. So now let us put this also in the, this is hint just for observation for you. I will give one equation. That equation was actually equation 5. Now this equation is actually 6. This is all about the Faraday experiment of case 1. Case 1 is actually non-moving loop area uh, is present in the time varying magnetic field. Now let us go to the second experiment of the Michael Faraday, that is case 2. In case 2, the loop area was moving. Then if loop area moves, then loop area changes, but in the static magnetic field, that means magnetic field is not a function of time. So a moving loop area is present in the static magnetic field. Then EMF is induced in the loop. This EMF is called as motional EMF because loop is moving, no, that is why motional EMF. This EMF is given by putting equation 6 in 5. So that equation 6 is this one, and equation 5 is EMF is equal to closed E dot dl. Actually that E bar is this one, V bar cross B bar dot dl bar. So this is motional EMF actually, equation number 7, students. So here is that equation, EMF is equal to closed E dot dl. In place of V bar cross B bar is kept. That means V bar is velocity of the conductor. We will see that. I will show you the diagram also. Don't worry about that. Now, if V bar comma B bar are uniform. Uniform means they are not functions of distance. Uniform means V bar comma B bar are not functions of distance. Okay, that is the meaning. But they can be function of time, no problem. So if V bar comma B bar are uniform, then EMF is equal to V bar cross B bar comes outside. So single integral dl bar, that is nothing but V bar cross B bar dot dl bar, integral dl bar is nothing but L bar. So EMF. Okay. Now I am going to what do you say, in case 2 there are again 3 different situations. So in case 2, first one is like this. I am making the diagram. This is called moving rail, RAIL rail experiment. Here RAIL rail means that is one conductor actually. You see the situation. So here there is a one conductor and second conductor, third conductor. Okay. Now I will take this as a z axis. I will take this as a y axis. Now here this is x axis is out of the board. This is y axis. This is z axis. These are conductors actually. conductor. Now there is a one moving conductor here. Like this it is moving. This is moving conductor. So it is moving like this. The moving velocity is equal to some v0 velocity. Moving like this means minus ay. Am I right? Minus ay. It is moving like this. It is like this means ay opposite. Like this it is moving. Now here inside this now actually this is conductor, this is conductor, this is conductor. If this conductor is moving like this, then area of this loop changes actually. So in this changing loop area, everywhere magnetic field is there, but that magnetic field is like this away from the board. At single location I have shown B is there, but it is not a function of time. So B bar is equal to, let us say, B naught into, like this means out of the board AX cap. Okay. Now there is one conductor here. So let us say the conductor length is L. L is the length of that. Then L bar of this is L into AZ. So this is Z direction. L into AZ. L bar is equal to, where L is length of this conductor. Okay, length of this moving conductor. Now let us apply this one to this case. If this conductor has some resistance here like this, some resistance is there, then EMF is induced here. Then we want formula of that EMF. How much EMF is induced here? So now once again I am describing this. L length conductor is moving with V velocity in the static magnetic field. Then how much EMF is induced in this? This is the formula for that. Here V naught means constant, not a function of distance. B naught means that is also constant, not a function of distance. That means they are uniform. Let us apply this. EMF is equal to, this V bar is V naught minus AY cross B bar is B naught AX cap dot L bar is there. Now this is equal to V naught into B naught into minus of AY cross AX is AZ. AY cross AX is minus AZ, minus into minus plus. So it becomes AZ. Now dot L bar is L AZ. Now AZ dot AZ is 1. You get V naught, B naught, L. So dear students, here how much EMF is produced? Simply VBL. So this VBL formula when will you use? Whenever V bar is in plus or minus Y direction, B bar in X direction, and L bar in Z direction, Z, Y, X, AX cap, AY cap, AZ cap, they are mutually perpendicular. My dear students, if you want, you can write, I am not writing. If V bar, B bar, L bar, they are mutually perpendicular, and V and B are uniform, then how much EMF induced? VBL is the formula. Don't forget that one. In examination, you see this type of diagram, na? You should not ask me to explain that. Already explained. Now, how much EMF is induced? VBL EMF is induced. So, where V is a linear velocity of the moving conductor, then L is length of moving conductor. B is static magnetic flux density. Okay. Now I am going to explain another one here. Once again I am telling, when will you use this? VB should be uniform and VBL should be mutually perpendicular. Okay student. Now let us see the second case. Actually in this case, here let us talk of cylindrical system. Cylindrical system. Okay, I want this formula also. Okay, let it be like that. If it is required, we will see that. Second case is, let us assume that that static magnetic field is in z direction. Which direction? Z direction. Okay, in this we have taken z direction. Now we will take in cylindrical system. That means that will be in rho direction. I will draw the picture, you will understand. You see this one? This is z axis. Now there is one magnetic field source here. Then that magnetic field source is generating the magnetic field in radial direction like this. That means that is rho direction, students, in a cylindrical system. So here I will write here that B bar is equal to B naught into A rho cap, radial direction that is. So here also it is there like this. Everywhere it is there, student. It is radially outward here like this. Okay, like this. Now there is one conductor here of length L, so that here L bar is equal to L into AZ, because L is length of this and AZ it is parallel to Z axis. Okay. Now it is rotating with omega is equal to 2 pi f angular frequency. Rotating means like this. I am showing this is Z axis, this is the conductor, it is rotating like this. Whenever it rotates, this is Z axis and this one is magnetic flux radially outward, and this conductor is rotating. Whenever this conductor rotates, then this magnetic flux crosses this one, so that EMF is induced in that. Now this has some resistance here, EMF is induced in this. This conductor is rotating in the circular path like this. Okay, like this it is rotating in the circular path like this. Now student, it is rotating with the f frequency. Then every time this cuts the magnetic field. So this conductor has some resistance and it is rotating with the f frequency. Then the angular frequency is 2 pi f. Then EMF is induced in this. Now if this picture is given in the examination, then what formula to be used? Then I will tell you. Now let us say the radius of this circular path is r, then you students should understand the velocity is in this direction. Velocity v bar is equal to r omega into a pi, student, here. So this is what? Pi direction. In cylindrical system we are talking. So and this v bar is linear velocity. Actually here v bar is linear velocity. Now for circular motions, that v becomes r omega. How it becomes r omega? If you want, I will write here. V is equal to meter per second, that means length divided by time. So here circular path length is 2 pi r divided by time. Now 1 by time is frequency, actually 1 by time is frequency, so 2 pi f into r, so 2 pi f is omega, so r omega. Okay. Now this v bar is equal to r omega into a pi. My dear students, in cylindrical system, aero cap, a pi cap, az cap, they are mutually perpendicular. That means b bar, l bar, v bar, they are mutually perpendicular. And also b naught means constant, r omega also here. Once frequency is fixed, radius is fixed, this is also constant. So that means they are uniform. Then if they are mutually perpendicular and uniform, this VBL formula can be used. So once again, how much EMF is induced in this? So EMF induced is equal to, once again, VBL. So magnitude of V is R omega. Magnitude of B is B naught. This is L. So this much EMF is there here. Once again, this formula is used. Whenever you see this diagram in the exam, then how much EMF is induced? This is the formula. Okay. Now third case, student. This is z-axis and this is y-axis. Out of the board is x-axis. Now everywhere here, like this, here also, student, everywhere here b bar is there. That b bar is equal to b naught into az. B bar is there here. Not means, b naught means not a function of time, static field, that is here b bar is there like this. Okay. Now there is one loop here. It may be rectangular loop or otherwise it may be circular loop, doesn't matter. So one loop is there here like this. Now that loop has some radius r or otherwise rho also, no problem. Now this loop has some resistance here. If this loop is like this, no, student, if this loop is like this, no, some resistance is there, finite resistance. But if loop is like this, means it is open, here infinity resistance is there. So this loop may be like this or may be like this. If loop is like this, means that resistance of this loop is finite. If this is open, means the resistance of this is infinity. Anyway, both of them have some resistance. Wherever resistance is there, their EMF is induced. So here EMF is induced in this loop. Now this loop is rotating with omega is equal to 2 pi f rotational frequency or angular frequency. Angular frequency is 2 pi f. Now here also EMF is induced. We need formula for that. How much EMF is induced? We need formula for that. Actually, I will show you this picture. The picture is like this. B bar is like this. Be careful. This B bar is like this. Okay. Now here one loop is there. This one. Here one loop is there like this. If this loop is parallel to this B bar, then induced EMF in this loop is 0. Now if this loop is rotating, then some amount of magnetic flux crosses. So small amount of EMF is produced. Then loop is rotating like this. Then more magnetic flux crosses, more EMF is produced. If that loop is like this, maximum magnetic flux crosses this, more EMF is produced. Now again the amount of magnetic flux crossing this loop is decreasing. Now again the amount of magnetic flux crossing this loop is 0. That means here sine and cos signals are generated here, because this one, if loop is like this, then 0 EMF. If loop is rotating, EMF is increasing, maximum EMF. Again EMF is decreasing. So loop is rotating like this, no? Now, if this loop rotates, then B bar and S bar of this loop make some angle. That angle is called theta BS. That theta BS is a function of frequency and time. So now this B bar, and there is a loop here. That loop has some area. That loop has some area. This is the area. The surface vector of this loop is this one. Then B bar is this one. If the loop rotates, then what happens? This surface vector, and if loop is rotating, then this surface vector also rotates. Then angle between B bar and S bar also changes with respect to frequency and time. So now here theta BS, theta BS becomes omega t. Okay, so if loop rotates in static magnetic field, then angle between B bar and S bar changes of course changes, okay, changes, and that gives theta BS is equal to omega t. Okay, student. Now we need a formula for the how much EMF is induced here. Then answer is EMF is equal to, in this case, no student, this is the formula for that. Okay, this is the formula. Here B is there, but it is static. That B is static. In that case, B is static. And area also not a function of time. B is also not a function of time. They can come outside. And in place of theta BS, omega t you have to substitute. So EMF is equal to minus of d by dt B naught into area, then cos of theta BS becomes omega t. So ultimately B naught is not a function of time, area is also not a function of time, and d by dt of cos omega t, that is actually, what do you say, minus sin omega t into omega, it becomes let it be like this, dear students. So this is the formula. Okay, for circular loop, area is equal to pi r square. For rectangular loop is given, na? So for rectangular loop, in place of the circular loop, if rectangular loop is there, for a rectangular loop, area is equal to A into B. So in examination, if you see this type of diagram, then how much EMF is induced, you have to use this formula. So these are the cases. Okay. So in these three, first one and second one, third one, everywhere this B bar is static, but a loop is moving in different ways. Here sine or cos signals are generated. Anyway, now what is the Third experiment, combination of first one and second one. A moving loop area is present in the time varying magnetic field, then induced EMF in loop is sum of transformer EMF and motional EMF. If loop is moving, then motional EMF. If magnetic field is a function of time, then transformer EMF, both are present. So sum of transformer EMF and motional EMF. So in this case, total EMF becomes that transformer EMF is minus dpi by dt, and motional EMF is this one, closed V cross B dot dl. So both you have to add, students, that is this one. Okay, these are the three experiments. So students, now let us write one observation. This observation is Maxwell equation from the Faraday's law. Okay, so this Faraday's law is, mathematical equation is EMF is equal to minus of d pi by dt. This is equation number 1. Now, yesterday I told you by definition EMF is equal to closed E dot dl bar. There was a closed loop here. So inside a closed loop, single surface is there, that is called open surface. Now, by definition, magnetic flux crossing open surface is double integral b bar dot ds bar. This is equation number 3. Put equation 2, 3 in equation number 1, and this is closed E bar dot dl bar is equal to minus of d by dt double integral b bar dot ds bar. Okay. Now, this d by dt goes inside. If it goes inside, then closed E bar dot dl bar is equal to double integral minus of dou b bar by dou t dot ds bar. This is equation number 4. From, actually here double integral ds means integration with respect to distance variables. D by dt means with respect to time. Time and distance are independent. They don't depend upon each other. So they are independent. So that is why this d by dt can go inside the distance integrals. So d by dt goes here. It becomes minus dou b by dou t, minus also inside. Now from Stokes' theorem, closed E dot dl bar is equal to double integral del cross E dot ds bar. Now you substitute equation 5 in 4, substitute equation 5, put equation 5 in 4, then you get double integral del cross E dot ds bar is equal to double integral minus dou b by dou t dot ds bar. So here double integral ds is there, double integral ds is there. You compare both sides. Then we get del cross E bar is equal to minus of dou B by dou T. So this is equation number 6. Now this del has a dou by dou x, dou by dou y, dou by dou z. That means differentiation. That is why this is called differential form of Maxwell equation. This differential form of Maxwell equation came from Faraday's law. I will write these things in the note later on. This is just observation. Now, here differentiation with respect to distance is given importance because in this equation also d by dt is there, here also d by dt is there. With respect to time is not considered here, and here integration is there with respect to distance, and here integration is there with respect to distance. That is why this is called the integral form of the Maxwell equation. From this only you got this one. But in this there is no distance integration, there is a differentiation with respect to distance. In del, dou by dou x, dou by dou y, dou by dou z is there. So this is called differential form of Maxwell equation. Differentiation, to know the physical meaning of differentiation, you have to substitute the point. That is why it is also called point form or differential form. This is called integral form of the Maxwell equation. And these equations came from Faraday's law. You have to remember these three things. These equations came from which law? Faraday's law. And this is called integral form. This is called differential form or otherwise point form. These things I will write in the table later on. Okay. Now, let us talk of the continuity equation. That means what is the condition to have a continuous current? That is called continuity equation. So here continuity equation. That means what is the condition? Condition means some equation. What is the condition to be satisfied to have a continuous flow of current in the conductor? For example, you take the conductor like this. You take the conductor. You take the conductor bar. Dear students, this one is conductor. Here light. Okay. This is conductor bar actually. Now, let us say you are standing at this location. Let us say you are standing here. Why are you standing there? For observation. So, their current was going. Let us say this is inner region. Let us say this is outer region. Now, if this is outer region, wherever you are standing, to that reference, this is outside, this is inside. So, this one, you are standing here and you are observing there by standing. Now, here, let us say current In is equal to dq In by dt. Here, q in means charge inside this region. I in means current in this region. Let us say this current is going like this. And here is the current I outer region, I out I say. So here there is a conductor here, total one conductor is there. This conductor has volume. So around this volume there are 6 surfaces, and that is why it is called closed surface. So here we are dealing with a closed surface, or otherwise inside that closed surface volume is there. So there are total 6 surfaces for this conductor, solid conductor. That is why it is called closed surface. Inside the 6 surfaces there is a volume. So that is why in the derivation always we talk of closed surface and volume, dear students. That you remember one point. Second point is here current is going, let us say. Now I am standing here observing, I am standing at this location. I am standing at this location and observing the current flow. So here current is coming, here current is going. I am calling this as a inside region. This is outside region for this location. For this location, this is inner region, this is outside region. Now, for example, students, let us say here 6 liters of water is coming. 6 liters of water is coming here from this. 6 liters of water is coming here every time. That 6 liters of water should decrease in this side. So, whatever water decreases this side, let us assume this is a pipe. here 6 liters of water is coming, then this side that much water, 6 liters water should decrease every time. You want continuously 6 liters of water coming out here, then continuously here 6 liters of water should decrease. Decrease means minus actually. So here similarly, what is the condition to have a continuous flow of current in this picture? The condition is whatever is going out, that much should decrease here. Decrease means minus of. So here current is dqin by dt. So whatever value decreases here, that will be coming out here. So that is the condition to have a continuous flow of current. That is called condition to have a continuous flow of current. That is simply called continuity equation. Continuity means continuous flow should be there. So dear students, here once again I am telling, assume this is a pipe. ये पाइप मान लीजिए, इससे बाहर इस इधर से 6 लीटर पानी आ रहा है मान लो, हमेशा आते रहना 6 लीटर, फिर वो हमेशा इधर 6 लीटर आने के लिए इधर हमेशा 6 लीटर डिक्रीज होते रहना है. सो इसलिए मैं बोल रहा हूं, अगर इधर जो भी करंट आएगा आई आउट, उतना ही करंट इधर डिक्रीज होता ही रहना है हमेशा. इधर जितना करंट डिक्रीज होता है उतना ही करंट इधर बाहर आते रहता है, फिर वो दोनों इक्वल होता है. सो मैं इधर लिख रहा हूं, आई एम राइटिंग हियर condition to have a continuous flow of current. Condition to have a continuous flow of current is I out is equal to dq in by dt is current here, that much should decrease actually. So whatever current dq in by dt is that current, minus means decrease, whatever current decreases here, that much comes out. So this is the condition to have a continuous flow of current at this location. Okay, so this is we are observing with respect to distance, dear students. At this distance we are observing, but in the textbooks they don't write in this much detail. Simply they write condition to have a continuous flow of current is I is equal to minus dq by dt. So they write like this. In textbooks they write simply I is equal to minus dq by dt. Like this only they will write. They just for understanding purpose I wrote in, out and all those things. But in textbooks what they do, condition to have a continuous flow of current is I is equal to minus dq by dt. Simply they write. Dear students, I told you 6 surfaces are there. That means that is a closed surface. So you students know that what is the current definition in terms of closed surface when J bar is given. By definition current crossing closed surface is I is equal to double integral J bar dot ds bar. Now I told you already, again you should not confuse. Here there is a closed surface, that means 6 surfaces are there like your room, and inside that closed surface volume is there. That is why in the derivation we will talk of closed surface and volume. So here closed surface is taken. What is the current going out of the closed surface? Double integral double closed J dot ds. This is equation number 2. Similarly, by definition Q is equal to triple integral rho v dv. Dear students, inside this there is a charge. The current is flowing means charge is there. Where is that charge? In the volume. So that is why you are talking of volume charge density. And also current is going, divided by cross sectional area gives current density, and that current density also is present. That is why we are talking of that one. So this is equation number 3. Substitute equation, put equation 2 comma 3 in equation number 1. Now that becomes a double closed J bar dot ds bar is equal to minus of d by dt triple integral rho v dv. Now this becomes a triple integral minus of dou rho v by dt dv. So this one double closed j bar dot ds bar. So this is equation number 4, students. Now from the divergence theorem, double closed j bar dot ds bar is equal to triple integral divergence of j dv, dear students. So this is 5. Put equation 5 in 4. Then triple integral divergence of j dv is equal to triple integral minus of dou rho v by dou t dv. Now compare both sides. Now divergence of j bar is equal to minus of dou rho v by dou t. So this is equation number 6. So dear students, this is the condition to have a continuous current in terms of current and charge. This is also called continuity equation in terms of current and charge. This is also continuity equation in terms of current density and volume charge density. But anywhere in objective question they ask, no, one more is there, which of the following is the continuity equation? There are 3 equations and all are correct, like multi-select questions. So this is also condition in terms of current and charge. This is also condition. One more we will get. Let us solve that one. Now we know that in a conductor, J bar is equal to sigma into E. Current density is equal to conductivity into electric field. Now from substitute this one here, substitute 7, put equation 7 in 6. Now divergence of sigma E bar is equal to minus of dou rho v by dou t. Now sigma comes outside, so sigma divergence of E bar is equal to minus dou rho v by dou t. Now here it is assumed that homogeneous medium, for homogeneous medium, sigma is not a function of distance, so it can come out of the del. Del is having dou by dou x, dou by dou y, dou by dou z. Now one more equation is there, d is equal to epsilon E. From this E is equal to, E is equal to d bar by epsilon. Let us say this is equation number 8, this is equation number 9. You put equation 9 in equation number 8. Now sigma del dot E bar is d bar divided by epsilon, that is equal to minus dou rho v by dou t. So from this epsilon comes outside, sigma by epsilon divergence of d bar is equal to minus dou rho v by dou t. So already I told you one of the Maxwell equation is divergence of d bar is equal to rho v. I told this in the basics divergence concept also. I told you by units. No, I told you this is 1 by meter, coulomb per meter square. This is coulomb per meter cube. Dot product gives scalar. This is scalar. So this is equation number 11, student. Okay. Now you substitute equation 11 in 10. So put equation 11 in 10. And sigma by epsilon divergence of d, that is rho v, and minus of dou rho v by dou t. You get this side, so you get dou rho v by dou t plus sigma by epsilon rho v is equal to 0. Equation 12, this one. Okay. So I told you in multi-select question, students, which of the following is the continuity equation? So Three options are correct. In first option, this one is there, I is equal to minus dq by dt, but this is the continuity equation in terms of current and charge. This is also correct. In second option, this is there. This is also correct. It is in terms of current density and rho v. In third option, this is there. This is also correct. It is in terms of rho v only. Okay. Now, based on the solution of the differential equations, you can write this one like this: d rho v plus epsilon by sigma rho v is equal to 0, where d is equal to d by dt, and d plus sigma by epsilon rho v is equal to 0. Here root is d plus sigma by omega epsilon 0 implies d is equal to minus sigma by epsilon. I am directly writing now solution of equation 12 is this numerator variable, that is rho v. Rho v is equal to some constant. One root is there means one constant. This already you know. I am not explaining much. This I am assuming you know this one. So now exponential, the root is minus sigma by epsilon into, here denominator variable is t. Okay. Now let us say this is 13. Now let at t is equal to 0 time rho v of t is equal to 0 is rho naught. Definitely at t is equal to 0 time, some volume charge density will be present, definitely, there is no doubt. That volume charge density is called as initial. Initial means starting time. So initial volume charge density. So actually this is the solution of rho v and is a function of time here. So here rho naught is initial, that means starting time, initial volume charge density, coulomb per meter cube. Now if you substitute this one here, and rho v of 0, t is equal to 0 means c into e power 0 you get. We are taking this as a rho naught. So here c is actually rho naught. Now that equation becomes rho v of t is equal to c is rho naught and e power minus of t divided by, I will write like this, e power minus t divided by, this comes here epsilon by sigma minus of, and this is also written like this, rho naught into e power minus t divided by tau r. So this is the solution. This one is called solution of the continuity equation. This is called solution of the continuity equation. Now it is like capacitor charging equations, discharging equations, you know, in the network theory. Similar to that, here time by time, exponential is a number, so here unitless it should be, time by time it should be. So this is a constant epsilon and sigma constant for the conductor, so that ratio is also constant. It should have unit of time because here time is there, so it is called time constant. That is called relaxation time constant, where otherwise I will write here equation number 14. Equation 14 is the solution of continuity equation. Okay students. Now here tau r is equal to epsilon by sigma. Of course this is called as relaxation time constant. So you know that in network theory, RC is also called time constant. If R is the resistance of that conductor and C is the capacitance of that conductor, then sigma by epsilon by sigma is nothing but R into C. So this is time constant, no student. If you want to, you can see that I will do like this, na. R into C. R is equal to actually rho L by A. So rho L by A, that means L by sigma A. Now capacitance is equal to epsilon into A by D. D is taken as L here. Now after cancellation, what will you get? A cancel, L cancel. So you get epsilon by sigma. So that is why in textbooks they write RC is equal to epsilon by sigma. So this is a relaxation time constant. This also you have to remember, and this one also. If this is the conductor material permittivity epsilon and this is conductivity, the ratio is equal to resistance of the conductor bar and capacitance of the conductor bar product, that is. This is called relaxation time. So what you have to remember for objective questions, those three equations, and this is the solution, and what is relaxation time constant, and whenever t is equal to 0, then rho v of t is actually rho naught. Whenever t is equal to tau r, then rho v becomes rho naught by e. Rho naught by e. If you want the diagram, na, I will draw this diagram here like this, students. Here rho v of t, this is time. When time is equal to 0, that value is actually rho naught at time is equal to 0. Whenever time is equal to tau r, now that value becomes rho naught by e. For example, here let us say this is rho naught by e, or otherwise rho naught into e power minus 1, dear student. So this is rho naught, and here rho naught into e power minus 1, e power minus 1. So whenever t is equal to tau r, that value is rho naught into e power minus 1. So now that equation is going like this, okay, like this it is decreasing. So whenever t is equal to 0, then value is rho naught, rho v of t here. Whenever t is equal to tau r, so this is e power minus 1. So rho naught into e power minus 1 at this time, this value is this much. Okay, it decreases exponentially.